We've discussed a little bit about integrals and antiderivatives. Today we're going to talk about a different type of integral, which is called a definite integral. And I'm first going to tell you what an indefinite integral is. So an indefinite integral is going to give you the antiderivative of a function. I gave an example here. The integral of 5x dx is equal to 5x squared over 2 plus c. Now, a definite integral you might like a little bit better because not only does it not have the plus c in it that you have to remember to put in, but you're also going to have a definite answer. You're going to get a number as an answer. And this number is going to represent the area under a curve. So in the previous section, we were doing Riemann sums. Now, Riemann sums are, they're great. A lot of calculus was built on them. However, they're not really very practical. As we take the limit of a Riemann sum towards infinity, we actually get a definite integral. I'll give you a definition here. So a definite integral has this definition below. This is pretty much the standard definition that you'll get in any calculus class. Most calculus definitions actually start off with something along the lines of if f is continuous. That's why we spend so much time in the beginning of the class talking about continuity. So if our function is continuous, then the area bounded by your function and the x-axis is the definite integral of f of x dx from a to b. And a and b are always x values. So like it'll be a is here, b is here. And if my function is like that, that's my f of x, then this integral represents this little area right here. I'd like to relate definite integrals with Riemann sums. And if you recall from the last section, when we had a function, we could find the area underneath that curve by breaking it up into rectangles. So let's say that I had n equals 3 for this one, and I broke it up into rectangles that look like that. So these three rectangles would give me an estimate of the area from 0 to this point right here. And I'm going to call this value x1, or actually I'll call this x0, I'll call this one x1, x2, and x. So the other thing that we had was that this partition width was called delta x. So for this one, I'm going to give you the formula, but I want you to understand the formula a little bit, so I want you to remember where we got it. So each rectangle is going to have an area equal to delta x times the height of that rectangle, and it's going to be, I'm going to say f of x sub I. And when we added up the total area, the total area was, this would be f of x sub 1 times delta x plus delta x times f of x sub 2 plus delta x times f of x sub 3. So the formula for that is going to be I equals 1, the sum from I equals 1 to n. In this case, my n was 3 of f of x sub I times delta x. So in the situation that we just had, we had, and you can see right here, we had n equals 3. So I'm hoping that if you look at this formula really closely, you can see that from the summation on the bottom, we ended up getting that area on the top when n was equal to 3. Now, in order to get a better approximation of an area, like in this one, the area approximation is not very good. We have these empty spaces here that are not taken into account when we do that right Riemann sum there. So we don't like to have those empty spaces. If you do more rectangles, you are going to get a better, estimate. So if instead of doing these 3 rectangles, I were to break it into 6 rectangles, then I would get a much better estimate of the area. I'm going to kind of overlay them here. So you can see that with the yellow rectangles, I have a lot less empty space, and that gives me a better area. Now, doing it this way it's not really very practical. It would be really, really, really long if we were to find the area with many, 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 many rectangles. However, we have a way to approximate this area. So what we're going to do is we are going to get our best approximation for the area when n approaches infinity. So what we're going to do is we are going to take a limit of this. So our area here is going to be the limit as n approaches infinity of this sum right here. So you might be wondering, how is this all related to a definite integral? Actually, this is the limit definition of an integral. So if you see something like this, this is, if you have a limit that approaches infinity of a sum, it's likely that that is going to be the integral. And so as far as our integral is concerned, this sum part right here is equivalent, not including the f, I kind of accidentally included that. That's equivalent to our integral symbol. You might notice that our integral symbol looks like a stretched out S. That's not a coincidence. The S stands for sum. So the f of x is still going to be inside of it. This delta x, rather than writing delta out every time, we write dx instead. So that's actually where the dx comes from. It comes from that delta x. And actually the a and the b, the a is going to be equal to the starting point. In this case, it would be x0. The b is equal to the ending point. In this case, it would be x3, which is also going to be, that's going to be like our x sub n. This is going to be our x sub 0. All right, so if you're looking at this and you have no idea what I was just talking about, you're probably going to be fine. I would like you to kind of see where the idea of a definite integral comes from, but if you're a little bit confused, you're probably going to be okay. So I'd like to go over a few important definite integral properties. And I put the general definite integral on the side just for reference. So first of all, you'll notice at the bottom we always have our a, and at the top we have our b. So in order to evaluate a definite integral, you must make sure that a, or whatever is on the bottom, is going to be always going to be the leftmost, meaning leftmost on a number line, or you can think of it as the smallest value. So it's important that when you're finding an area under a curve, that's what a definite integral does, that we evaluate it from left to right. So if you find that your the b, the thing on the top, is smaller than a, you're going to have to switch them around. And the way that you're going to switch them around is by making them negative. I'll write this out. If b is smaller than a, we say, because we always evaluate it from left to right, if your b is smaller, then it's kind of like we're moving backwards. And when we move backwards, that means we're going to have a negative. It's the best way I can think of to explain it. So I'll give you an example. If you have, first of all, I'll show you the formula. That's probably what you really, really want. So if you have something where your bigger number is at the bottom, you're going to have to switch them around. But in order to switch them, you have to make your integral negative. So that's our first important property. So for example, if you have the integral from 4 to 7, we actually can't evaluate that integral as is. You have to switch it around. You're going to change it to 7 to 4. Okay, so that's our first property. This one, this is property number 1. It was super long. Property number 2 is that if you have an area above the x-axis, it's going to be positive. If you have one below it, it's going to be negative. So I'm going to draw a little diagram for the next two. So let's say you have a function. This is A, this is B, and this is C. And those are 3 x values. First of all, if you have an integral that goes from one value to the same value, if you think about what's the area between A and A, there is no area between A and A. That's actually going to be 0. So if you have one value to itself, you get an area or definite integral of 0. If you have an integral from A to C and there's a point like B over there in the middle, you can actually find the A to B and the B to C separately and then add them together. So we're going to do an example. You can see I have a graph. There's a lot going on this graph. Sorry about that. There's a bunch of little areas. By the way, keep in mind that the area that we're talking about is between the function and the x-axis. So it's going to be these shaded parts right here. I'm actually going to erase the stuff I just shaded just so you can see it a little bit better, but keep in mind that that's where the area is. Also, we know that the definite integral is an example, that is the area. So that's how we write the area. I'd recommend that you pause the video, maybe copy it on the picture if you want, and I want you to see if you can try some of these on your own. Some of them kind of just use logic, others use the properties that we just had. So give them a try. It's okay if you get them wrong the first time we're doing it. Okay, so for number 1, the integral of f of x dx from 0 to 1, that I told you on the side that the area underneath this shaded area right here is going to be 2. So the answer for that integral is just 2. From 0 to 4, you need to add together the area in the first part where the 2 is with the area from 1 to 4. That is going to be 2 plus 6 is going to be equal to 8. For number 3, I asked you to find the area from 1 to 6. Actually, before we do that one, I want to do 4. I kind of mixed up the order and put them in the wrong place. For number 4, the area from 4 to 6, you can see I put that the area is 3, which is almost right. However, if you remember, I did say that areas below the x-axis are negative, so the answer for that one's actually going to be -3. So be really careful about that. Now I'm going to go back to 3. The area from 1 to 6, I'm going to add up the area that's 6 from 1 to 4, which that's that first part. And then I also know from 4 to 6, it was -3. So I actually do need to do 6 minus 3. So the answer for the integral from 1 to 6 is actually going to be 3. For number 5, the integral from 4 to 8. From 4 to 6 is -3. From 6 to 8 is 7. So I get -3 plus 7, which gives me 4. 6 is one of those ones that I mentioned earlier where you need to change the order. The smaller number needs to be on the bottom. So in order to get the smaller number on the bottom, I am going to make this integral negative. So I get negative integral, sorry about that negative, it's hard to see what's going on there, of f of x dx. We know that the integral from 1 to 4 is the area from 1 to 4, which is 6. So my answer for that is -6. For number 7, that is the full area for the entire graph from 0 to 8. So I just need to add up all those areas. So I get 2 plus 6. Keep in mind the 3 is negative again. And then I have plus 8. So the answer for that one ends up being 12.